In this video, we are going to learn about two new elements of graphing rational functions, holes and slant asymptotes. I am losing my voice, so I apologize in advance that my voice sounds this way, but I'm going to do my best, so I hope you will bear with me. Vertical asymptotes were simple. We just set the denominator equal to 0 and solve for x. And that never changes. Horizontal asymptotes were a bit more complicated. You've seen this 100 times. For horizontal asymptotes, we had to stop and think about the degree of the numerator versus the degree of the denominator. And we fell into one of three situations. If the degree of the numerator was less, then the horizontal asymptote was y equals 0. If the degree of the numerator was equal to the denominator, then the horizontal asymptote was found by dividing the leading coefficients. And if the degree of the numerator was greater than the denominator, then there was no horizontal asymptote. Now, I've been mentioning to you that there was another possibility, and I always said I would tell you later what that was. Well, guess what? Today's the day. If the degree of the numerator is exactly 1 greater than the denominator, then yes, there's no horizontal asymptote. However, there will be a slant asymptote, a diagonal asymptote. And we will find that asymptote by doing division. I don't know why I said long division. It doesn't have to be long division. It's just any kind of division. Long division, synthetic division. In fact, we will often do synthetic division. Anyway, we're going to ignore the remainder, and that will give us the slant asymptote. So from now on, there are sort of 4 situations that we're going to think about. Let's look at problem number 1. We are supposed to find all holes and asymptotes. I haven't told you about holes yet, but there are no holes on problem number 1, so we can worry about that later. But we're going to find all asymptotes. But from now on, we're going to watch out for slant asymptotes as well as vertical and horizontal asymptotes. So first, good old-fashioned vertical asymptotes. Vertical asymptotes we would find by setting the denominator equal to 0. So let's do that. If we set the denominator equal to 0, then of course we would subtract 1 from both sides. That would give us x squared equals -1. But then we would want to take the square root of both sides. Don't forget your plus or minus. But right here we see we're about to get imaginary solutions. That means there are no vertical asymptotes. This is plus or minus I. Alright, imaginary numbers will not cause asymptotes. So as far as vertical asymptotes go, we're just going to say none. Okay, now let's move on to horizontal asymptotes. And again, we look at the degree and see which one of these situations we fall into. So let's see. The degree of the numerator is 3. The degree of the denominator is 2. So obviously the numerator degree is more than the denominator. Alright, that puts us in situation number 3 in the sense that there is no horizontal asymptote. But from now on, whenever the degree of the numerator is greater, fine, there's no horizontal asymptote. But is there a slant asymptote? Is the numerator degree 1 greater than the denominator? Well, this is 3 and this is 2. So this is exactly 1 higher. So there should be a slant asymptote. So in terms of horizontal asymptote, we're going to go ahead and say none. But we are going to look for the slant asymptote, and there should be 1. Okay, and the way we find a slant asymptote is by doing division. Now, one can either do long division or synthetic. But as we go and set this up, well, could I do synthetic division with a problem like this? The answer is no. You can't do synthetic division when it is squared. You're only going to do synthetic division when you have, like x plus a number or x minus a number. That's about it. Technically, you could do it, if you had anything linear, like 2x minus 3. But it's more of a hassle than it's worth, and you might as well do long division. So we're only going to do synthetic division when we just have, a linear with a leading coefficient of 1. X plus something or x minus something, that's it. So let's do long division. Everybody loves long division, so just don't pretend that you hate it. So I've got x squared plus 1. And I'm going to divide that into this trinomial. Be careful. There's a missing term here. Do you see it? We're going from squared to a constant. So there is an x term that's missing. So we're going to need a 0 in there. So I have x to the third power minus 7x squared. Here comes the 0 term. I'm going to show it in pink. So 0x. And then plus 9. Okay, once we do this, the slant asymptote should be the quotient that will appear right here. The slant asymptote does not include any remainder, so just ignore that. So let's remember how we do long division. We ask ourselves, we say x squared times what will give us x to the third power? Well, that'll be x squared times x. I'm going to line that up with my like term. Then I take this x and I do the distributive property with it, like this. So x times x squared, that's x to the third power. And then x times 1 is x, which would go here. Line up your like terms always. But then we change the signs in order to subtract. So that's going to become minus, and that's going to become minus. Obviously, these will cancel out. This is going to wind up coming down. So I have negative 7x squared minus x, and then plus 9. And then you sort of start over. So you ask yourself, x squared times what is going to give you negative 7x squared? Well, that would be negative 7. X squared times negative 7 will give you negative 7x squared. Once you have this, then once again, you do the distributive property with it. So you're going to go negative 7 times x squared and get that negative 7x squared that you wanted. And you're going to do negative 7 times 1 and get negative 7. Again, make sure you line it up with your like terms. As always, we're going to change the signs in order to subtract. So that's going to become plus. So these will cancel. And then I'm going to have negative x and then plus 16. Now I've already reached the constant. That means whatever else I have down here is a remainder. But so for what we're doing now, this remainder doesn't matter. I mean, normally I would take it and I would go plus negative x plus 16 over x squared plus 1. And that's all the quotient. But only this part is going to be giving me the slant asymptote. Now the slant asymptote is a line. Think y equals mx plus b. So the slant asymptote is going to be the line y equals x minus 7. Okay, so there are no holes, which we'll find out later. So we have found there was no vertical asymptote, there was no horizontal asymptote, there was just a slant asymptote, which is this particular line. Now, let's take a quick peek at, what's that program called? Desmos. Desmos.com, or you could use an app on your phone. to see what this looks like. What does a slant asymptote look like? What does this look? Aren't you curious? I'm curious. Come along with me, boys and girls. Alright, so I've typed the function into Desmos, and here's what this weird graph looks like. Notice there is no vertical asymptote, there is no horizontal asymptote, just like we thought. But it does seem to be approaching some diagonal line. Now, I'm going to type in the line. We decided it would be the line x minus 7. So I'm going to type that in right now. And sure enough, you can see the graph getting closer and closer to this line, y equals x minus 7 on either side. Even though it seems to trace it, by the time it gets to the further out, in our minds we know that it never actually quite touches. And think about the line y equals x minus 7. Remember how you learned a graph? Remember how you learned that y equals mx plus b. Negative 7 is the y-intercept. So we would expect that if we look here at negative 7, sure enough, that's where this line crosses the y-axis. Okay, that's the minus 7. And then remember how the slope is the coefficient of x. And here this is like 1 over 1. So we'd expect this line to go up 1 over 1. And if you look at the graph, that's exactly what it does. From this y-intercept, it goes up 1 over 1. So this is indeed the line y equals x minus 7. And as predicted, the graph approaches it asymptotically. You did not know that was a word. Now you're smarter. All right, now it's time to learn about holes. Holes happen when a factor that would have caused a vertical asymptote gets canceled out. All right, holes happen when a factor gets canceled out. Let me show you what I mean. So we can factor this very quickly, that this is going to be x plus 3 and x minus 5, because we just did this a minute ago. Now this one here on the top, okay, let's see. This is 2x squared is going to be x times 2x. The 3 can only be 3 times 1. Now I'm trying to get 5x middle. Remember how I always say inner plus outer equals middle? Well, inner, I have 6x. Outer, I have 1x. I can get a middle of positive 5 if I have a negative 1 and a positive 6. Okay, so I'll have a positive 6 if I make this a positive 3. And here's my negative 1 for the outer. And 3 times negative 1 makes negative 3, so it makes sense. So now I've factored it. So normally, I would have two vertical asymptotes, one at negative 3 and x equals positive 5. But as you just saw a moment ago, when a wannabe vertical asymptote gets canceled out, it's not going to be a vertical asymptote anymore. It is going to be a hole. So, asymptotes. We have a vertical asymptote, only one, and that's going to be x equals 5. We'll get back to horizontal asymptotes in a second. And slant asymptotes. We'll come back to that. But let's go ahead and talk about holes. There's going to be a hole at negative 3 instead of a vertical asymptote. Okay, as always, I'm taking that factor of x plus 3, I'm setting it equal to 0. That's where I'm getting the negative 3 from. Now, this hole is an ordered pair. Ultimately, when we do our graphs, we're going to graph a hole as a open circle. So we're going to have graphs that look like this. This type of thing. Okay, that's how we're going to show a hole. But, it's an ordered pair. We're going to need Well, that wouldn't be negative 3, but you get the point. No pun intended. So we need the y value to go with this x value. How did I say we're going to get that? If I type in my original function, I'm going to get an error at negative 3. So what am I going to do? I'll tell you what I'm going to do. I'm going to type in the bootleg function. Okay, the version where we canceled out the x plus 3. I don't know why I'm calling it bootleg. There's nothing wrong with it. I just feel like it's fake because it's not showing all the information. But it will help get us the whole, so I shouldn't hate on it. Anyway, I'm going to put 2x minus 1 in my calculator. So 2x minus 1. By the way, my voice hurts when I can't bring myself to say TI-30X as multi-view. Instead, I just say calculator. I must be hurting. X minus 5. Okay, I will use this to find it. So I need to know what's happening at negative 3. So if I want to go faster, I'll tell it to start at negative 3. So there it is. At negative 3, I've got 7/8. So that's what I'm going to put. Leave it as a fraction. I don't want the decimal here. Now, let's talk about horizontal asymptotes or slant asymptotes. By the way, to be clear, you're never going to have a horizontal asymptote and a slant asymptote. It's going to be one or the other. So, in this case, will there be a horizontal asymptote? Well, yes, there will be. It's all about the degree. The degrees are the same, 2 and 2. Recall that when the degrees are the same, that's when you get the horizontal asymptote by dividing the leading coefficients. So the horizontal asymptote is going to be y equals 2 over 1. So that's going to be y equals 2. Okay, that means there won't be any slant asymptote. All right, slant asymptote only happens when the top degree is 1 more than the bottom. So this is what we got. All right, let's take a quick peek at Desmos and show ourselves that there's only one vertical asymptote, not two, at vertical asymptote at x equals 5, horizontal at 2, and we'll look for the whole. So here's our vertical asymptote at 5, horizontal at 2. Notice there's just the one vertical asymptote. Okay, but at negative 3, we're supposed to have a whole, so let's check that out. I gotta get on here. Okay, so here I go, getting closer, and there it is. Negative 3, we are undefined. Okay. All right, let's try number 3. Now, to do this, we need to factor the numerator and denominator as far as possible. I can tell there's going to be a slant asymptote because the degree of the numerator is exactly 1 more than the denominator. But as far as finding wholes, I need to factor and see if there's anything that's going to cancel out or not. So, what do you want to do first? Should I find the slant asymptote first, or try to factor and find wholes first? All right, I think I'll find the slant asymptote first. So to find the slant asymptote, you're going to do long division. So I got x squared minus x minus 2. All right, and in here I've got x to the 3rd power minus 2x squared plus 7x minus 14, 3, 2, 1, 0. Nothing's missing. So let's do our long division, which everybody loves. X squared times what gives you x to the 3rd power? That'll be x, and I like to line it up with my like terms. I will take this and do the distributive property. X times x squared, x to the third power. X times negative x is negative x squared. X times negative 2 is negative 2x. All right, to subtract, we change the signs. So this will be minus, and this will be plus, and this will be plus. So these cancel out. So let's see, I've got negative x squared, and then plus 9x, and then minus 14. Okay, so I sort of start over. And I say x squared times what will make negative x squared? Well, that's going to be negative 1. And I will take my negative 1 and do the distributive property. So negative 1 times x squared is negative x squared. Negative 1 times negative x is positive x. And negative 1 times negative 2 is positive 2. All right, I could change the signs like you do. So that's going to make this 8x minus 16. But I've already reached my constant. So this is now the remainder. So that means this quotient, not including the remainder, this is going to be my slant asymptote. All right, so my slant asymptote is going to be y equals x minus 1. So I might as well get my little list going. So I'm going to have slant asymptote y equals x minus 1. The degree of the numerator is higher, so you will never have a slant asymptote and a horizontal asymptote. So horizontal asymptote, none. But what about vertical asymptotes and holes? So for that, I need to factor everything. So that's what I'm going to do. Let's see, how much room do I have here? So grouping. I can already tell that grouping is going to work on this particular problem because negative 14 divided by 7 is negative 2. And negative 2 divided by 1 is negative 2. So grouping is going to work. So let's go ahead and do grouping. Okay, so if I group these two terms and these two terms. So my GCF here is x squared. So if I pull that out, I'm going to have x squared. And then parentheses, I'm going to have x minus 2. Okay, now I'm betting I'm going to have another x minus 2 over here. Okay, the GCF here is 7. So I'm going to pull out that plus 7. And sure enough, 7 times x is 7x, 7 times negative 2 is negative 14. Now, this pink part is itself a GCF. So, as always, I will pull out this common factor of x minus 2. That's going to leave behind x squared plus 7. So this is how the numerator factors down. Okay, what about the denominator? So let's see. If I look at if I look at the denominator, okay, this is probably going to factor as a binomial times a binomial. Okay, so x squared can only factor as x times x. All right, 2 can only factor as 2 times 1. All right, I'm shooting for a negative 1 middle. So I'm going to need a negative 2 and a positive 1. Okay, so putting this factored numerator together with this factored denominator. let's see what we've got. Just going to put it down here. Okay, so we factored the numerator and we factored the denominator. So in this factored form, we would normally think that there would be two vertical asymptotes. But as you can see, the factor of x minus 2 is going to cancel out. When a factor cancels like that, that's where you get wholes from. Okay, so we're going to have a vertical asymptote. Okay, but we're only going to have one. All right, we're going to have a vertical asymptote that's going to come from this. And that's going to give me x equals -1. Okay, but we're going to have a hole because of the canceled factor. We're going to have a hole. Okay, so instead of having a vertical asymptote at x equals 2, we're going to have a hole at x equals 2. Okay, but we're not going to put x equals 2 because that would be a line. A hole is a single point. So we're going to put 2 as the x value, and we need to find the y value. Okay, we will find the y value by using what's left of the function. All right, after we canceled out the factor of x minus 2. So let's put this blue part in the calculator, and that's how we find the y value. All right, so here I am typing it into the calculator, and our hole is at 2, all right, which came from setting this equal to 0. So might as well tell it to start off at 2. All right, so at 2, I have a y value of 11/3. Please leave it as a fraction. Do not make this a decimal, because it would be imprecise and sloppy. Okay, so that's what we have. I'm going to quickly throw this into Desmos, and so we can see that there's no horizontal asymptote. Let's look for this slant asymptote and see what that looks like. There should be a vertical asymptote at -1. There should be a hole at 2. Let's glance at Desmos and see these features. All right, here's part of the graph at this scale. And so there is our slant asymptote, which we would expect it to have a y-intercept of -1 and go up 1/1. And there it is, doing exactly that. And you can see the function is approaching it. We were looking for a vertical asymptote at -1, and you can see it's approaching that. And there should be a hole at 2. So let me see if I can find that guy. All right, it's not letting me do it because as I'm getting too close, it's snapping to this low point right here. But you can trust that there would be, if I could get close enough to it, there would be a hole. Don't have time to force the issue. I'm going to zoom out a little bit so you can see a little bit more of the function. So you can see that there are 2 branches. There's one up here and there's one down here. But in both cases, it's approaching the diagonal asymptote and the vertical asymptote. Okay, and there you go. That's what this type of a crazy function looks like. We'll be graphing these by hand soon, so watch out for that. All right, look at number 4. Now, let's talk about the horizontal asymptote. Will there be one? Well, the top degree is less than the bottom degree. We've learned that when that happens, there will be a horizontal asymptote. It'll be y equals 0. So we've got that. That means slant asymptote will be none. That only happens when the top degree is 1 more than the bottom, so there won't be a slant asymptote. Will there be a vertical asymptote? Well, we don't know anymore. We used to just set the denominator equal to 0 and not worry about it. Now we have to worry about are things canceling out, so we need to factor first. The numerator has a GCF, so as I factor that, I'm going to get 2x minus 1. Okay, so this is interesting. So this x is going to cancel out one of these x's. So that would be like 2x minus 1 over x squared. So normally we might think, well, there's going to be a hole because we're canceling out x with one of the x's. So normally that would make a hole. But you know, that would be a hole at 0. You know, x is like just 0, because if you set x equal to 0, just get x equals 0. But if I set the remaining x squared equal to 0, if I take the square root of both sides, that's going to give me x equals 0. So we're still going to have a vertical asymptote. All right, because even after we cancel out the x's, we still have x equals 0. So we have a vertical asymptote at x equals 0. All right, and you can't have a vertical asymptote and a hole at the same time. It's already undefined because of the vertical asymptote. So there won't be any holes. So holes, whoa. Holes, none. Okay, so in summary, on that little detail right there, if you ever have a hole and a vertical asymptote at the same place, the vertical asymptote wins. There won't be a hole, it'll just be a vertical asymptote. Okay, so that's it for number 4. No time to look at Desmos for this one. This is taking too long. We're running out of time. So let's get to the back. So we notice that the top degree is 1 more than the bottom. Degree 2, degree 1. So that means there's going to be a slant asymptote. Is there a spot for that on here? So there won't be a horizontal asymptote. There will be a slant asymptote. So we'll just cross that out and put the word slant there. So how do we find the slant asymptote? We do some long division. So we're going to do x minus 2 divided into 2x squared minus 3x plus 1. So if we do that, we're going to have x times what makes 2x squared? X times 2x makes 2x squared. Distributive property, 2x times x is 2x squared. 2x times negative 2 is negative 4x. Change signs. Okay, so these cancel out. That leaves us with x plus 1. Start over. X times what makes x? That would be 1. And really, as soon as you got that constant, we can stop there. I mean, we could keep going, find a remainder, but this is going to give us our slant asymptote. Okay, that's why our slant asymptote is going to be y equals 2x plus 1. Okay. But you know what? I think I will keep going to see if there is a remainder. So if I do 1 times this, I'm going to get x minus 2. And then we would change signs, minus, plus. So I have a remainder of 3. Because there's a remainder, that means that x minus 2 does not divide evenly into this, which means that the x minus 2 doesn't cancel out. So there will not be a hole. Let's see, does this factor? Just to prove a point. But I already know that x minus 2 will not cancel out with anything. Otherwise, it would have been a remainder of 0. So 2x squared will only factor as 2x and x. 1 can only factor as 1 times 1. Inner plus outer equals middle. Inner, I have 1x. Outer, I have 2x. I can make negative 3 if I make both of these be negative. Boom, boom. That does give me positive 1, so that's how you factor it. But notice none of these cancel anything out. So I will have a vertical asymptote by setting this equal to 0, because it doesn't cancel out. So x equals 2 will be a vertical asymptote. And as I said before, there won't be any holes. Okay, how do we find x-intercepts? We can set the numerator equal to 0 for a problem like this. So it's helpful that we factored it, because if I want to set this numerator equal to 0, if I factor it, I'm going to wind up setting the factors equal to 0 to get my x-intercepts. So this is going to give me x equals 1, and this is going to give me 2x equals 1, and x equals 1/2, because I'm dividing by 2. So 1/2 and 1. So my x-intercepts are going to be 1/2 comma 0 and 1 comma 0. Okay, let's go ahead and graph what we have so far. First of all, we should have a slant asymptote at 2x plus 1. So let's graph that. So 1 should be the y-intercept, and then we'll go up 2 over 1 from there. So there's my y-intercept. Then I'm going to go up 2 over 1, up 2 over 1, like this. All right, this is going to be my slant asymptote. I can also go down 2 back 1, like this, to continue the pattern in the other direction. All right, so there's my slant asymptote. I also have a vertical asymptote at x equals 2, so let's go ahead and graph that. All right, we have x-intercepts to graph the at 1/2 and 1. So let's go ahead and do that. Okay, so I'm going to have an x-intercept at 1/2 and 1. Wow, that's really close together. Okay, so how about the y-intercept? To find the y-intercept, we let x equal 0. So that's what I'm going to do. If I let x be 0 here, that's going to wipe out this term. If this x is 0, that wipes out this. If this x is 0, so all I'm really going to have left for my y-intercept is 1 over negative 2. Okay, that's why my y-intercept is going to be 0 comma negative 1/2. Right, that's my 1 over negative 2. Uh-oh, my 0 is disappearing. All right, so 0 comma negative 1/2. All right, that's going to be right here. All right, so I'm going to need a few extra points to do this graph. I basically already see what's going on in here, but I need to pick points that are very close to the asymptote on either side. So let's go ahead and put this function into the calculator and see what it looks like. Alright, so here I have it typed in. I'm going to go ahead and be in ask mode so I can put in whatever I want. Alright, so I like to know what's happening just barely to the left and right of a vertical asymptote. So I see the vertical asymptote is at 2. So I want to know what's happening at 1.5. So at 1.5 we have -2. So let's go ahead and plot that. Okay, so that would be right here. Alright, that gives me a very clear picture of what's happening inside of here. Now, what about what's happening at 2.5, just barely to the right? Now, at 2.5, we're at 12, okay, which is already off my grid here. So 11 would be about here. So, alright, it's off the grid. I'm doing my best, okay, but that gives me an idea. Let's see what's happening at 3. I'm sort of wishing I had a bigger graph suddenly. At 3, I'm at 10. Okay, so at 3, I'm right here at 10. And what about 4? Let's just do one more. At 4, 21 over 2, it's 10.5. So at 4, I'm already heading back up a little bit. So this is off the grid. So I'm going to erase some of this mess that we used and we're done with. Okay, I'm going to extend out my slant asymptote so we can better see what's going on. Okay, so these 3 points that we plotted over here are enough to give us the idea of what's happening. So it must be approaching the asymptote in this type of way. Okay, and it's doing the same type of thing down here. Alright, so your graph would look very much like this for number 5. Last one. Let's look at the degree and think about whether or not there should be a horizontal asymptote or a slant asymptote. Well, the top degree is 2, the bottom degree is 1. The top degree is 1 more than the bottom. So that means we're thinking that there should be a slant asymptote. There's definitely not a horizontal asymptote, so I can forget about that. Now, I didn't want to confuse you with this before, but I have to mention it now for problem number 6. Sometimes, even though the top degree is 1 more than the bottom, there still is not a slant asymptote. And the thing is this, when you do your division, there has to be a remainder. If you do the division and it divides evenly with no remainder, that means what you really are looking at is a straight line, probably with a hole in it. So if you have a straight line, you can't call it a slant asymptote. It's just a line. There's no asymptote, it's just a line. So that's what's going to wind up happening on this problem. So I didn't want to confuse you with this before, but new rule. Let's see, where are my rules? To have a slant asymptote, there must be a remainder. If there's no remainder, the function is a straight line, probably with a hole. So let me show you what I mean. So if we do our division, x times what is x squared? That's x. Do the distributive property. X times x is x squared. X times -3 is -3x. Change signs. So these cancel out. So now I have 2x minus 6. And I start over. X times what will give me 2x? That will be plus 2. But watch what happens when I do the distributive property. 2 times x is 2x. 2 times negative 3 is negative 6. When I change the signs, of course, both things cancel out and I get 0. Because the remainder is 0, there's not going to be a slant asymptote. No slant asymptote. Instead, the entire function is going to wind up being a straight line. So to see what's happening, so over here I might as well just put none, because there won't be a slant asymptote either. To see what's happening, let's go ahead and factor this out and see what it looks like. Okay, I'm going to have to erase my words here to make room. So let's factor this out. The numerator, when I factor it, x squared is going to be x times x. 6 is going to be 2 times 3. To get a negative 1 middle, I need a positive 2 and a minus 3. And then you see in the denominator I have this factor of x minus 3. So see how these factors cancel out. Alright, that's why there was no remainder, because x minus 3 cancels completely away. So that's going to just leave us with x plus 2 as our remaining function. This is just a straight line. That is all. But the x minus 3, because it cancels, this is going to give us a hole, not a vertical asymptote. There's going to be a hole at x equals 3. So there's nothing left. There's our only potential vertical asymptote got canceled out. So vertical asymptote, we're going to say none. Okay, however, there will be a hole at 3. But we're not going to say x equals 3. We're going to say 3 comma something. Normally I would put this in my calculator, but this is so simple. It's just x plus 3. X plus 2. That's 3 plus 2 is 5. So there should be a hole at 3 comma 5. So to graph that, we will just plot an open circle at 3 comma 5. Okay, so there will be a hole. Now, so I can go ahead and just graph this remaining function because it's just a straight line. I don't need my calculator for this. This is just y equals mx plus b. It's just y equals x plus 2. So I'll have a y-intercept at 2, and then I'll go up 1 over 1 from there. So with a y-intercept at 2, and then I'll go up 1 over 1 like this. Now this is an open circle, so let's leave that alone. Okay, and I will graph it back the other way as well by going down 1, back 1. Alright, so this function is just going to be like a straight line. So I'm just going to connect these dots, but I'm going to leave this an open circle. So it should look like this. Alright, make your open circle nice and clear. Now, so obviously we have a y-intercept at 2. Okay, so that's 0 comma 2. But we can also see we have an x-intercept at negative 2 comma 0. Alright, that was pretty strange, so let's take one more quick peek at Desmos to make sure that we were right. So as you can see, the graph did in fact make a straight line. And you see the y-intercept is 2, and it's going up 1 over 1, just like we thought. And what did we say? There's going to be a hole at 3 comma 5. So see, can I trace this? So there it is. There's our hole at 3 comma 5.